So concavity, I usually just try to draw a couple pictures to explain concavity. And sometimes, just for future class reference, sometimes you hear people use the words convex versus concave. I don't know if anyone's familiar with those words. I don't like using those two contrasting words because sometimes it's confusing to remember which is which. And so instead, what I try to think about or use as words is just concave up and concave down. So if you're used to concave or convex, if you've heard this before, just know that I try to avoid that. And that's a pretty common thing, actually. People generally avoid that confusion by saying concave up and down. So anyway, concavity, I always think about a cave or something when I heard that word concavity, and that's kind of an apt description when you're thinking about what it means. So concave up, things that are graphs that are concave up, let me draw 3 graphs real quick, have a curvature that is upward facing. So an upward facing curve might look like this, for example, like x squared. But it doesn't have to be that drastic, right? So something like this, for example, is also concave up, or something like this with even slighter curvature is also concave up. And so when you hear the word concave up, you should just thinking it has upward facing curvature, like a bowl, right? Concave up. And so concave down, I'm sure you could imagine, is the same thing, but just downward facing. So we had a couple more graphs here. Let's do the same 3 graphs, just the opposite, right? So concave down then would be minus x squared, or something like this, or something like this. So it can be kind of slight, like the second two, can be drastic, like the first one, but it's an upside down bowl, right? You wouldn't try to dump your cereal into concave down. Okay, and it turns out the second derivative tells us about that curvature. That's why we're talking about it here, and that's why we talked about sort of higher order derivatives. I mentioned this, I alluded to this last time a little bit, and I'm glad we're just sort of putting this together with the first derivative test. So I'm going to explain how the second derivative does that, but are there questions about what I'm trying to say? Excuse me, about concave up or down? Okay. So again, that's sort of the definition, but this is the explanation about why that makes sense, right? So we know, make this a little bit bigger. We know this, right? We know that when we do a derivative, it tells us the rate of change. I hope we know that by now. Slope of the tangent line. And so if we do the derivative of the derivative, which we talked about last time, right? Second derivative, higher order derivative. What we mentioned last time, it tells us how the rate of change is changing. And we had called that acceleration previously. But let's think about it in this other kind of context, right? So the second derivative is how the rate of change is changing. So let's draw another picture. And let's say that the second derivative is negative at some point, A. So here's A. Let's draw a graph. If the rate of change is decreasing, maybe I should slide this over and write something here. Right, so second derivative being negative means the rate of change, f prime, is decreasing. In other words, the tangent lines are getting flatter. Maybe that's a better way to say it. Let me do that another color, i.e., tangent lines are getting flatter. If we have a graph where the tangent lines are getting flatter at a point over a certain interval, that means they used to be certain steepness, and then they're less steep. And so that might look like this. Right? Just kind of thinking about the tangent lines. Like the tangent line right here would be a certain steepness, but then a little bit after it would be less steep, right? The tangent lines are flattening out. The derivative's getting less intense. In other words, we end up with this downwards facing curvature, is what I'm trying to point. Right? We've got concave down, i.e., second derivative is negative. I'm just trying to like rationalize through why that second derivative gives us that curvature, because the slope of the tangent line is flattening out. And then the opposite's true if we have, I'll kind of do this a little bit quicker. If we have the second derivative being positive, the tangent line's getting more steep. And so that's going to do the opposite thing then, right? If the tangent line gets more steep at a point, it's going to end up doing a concave up thing, because we'll have like not a very steep tangent line and then a steeper tangent line, and that's going to make a bowl shape. Okay. And so this will tell us concave down. Oops. Positive. Okay. And so it's summarized below, but I would like to just see if there's, I know I say this a lot, but it's always just better in math if we understand why something's the case. If we just sort of make sense to us in our brain why the second derivative tells us concave down, because it's informing us about the first derivative, and we know what the first derivative means, like if that all just makes sense, you don't need to memorize anything, right? When the test comes around, you just show me that thing that you learned, and it makes sense. And it's fine to have to memorize things and have to study. I'm just trying to help you avoid some studying if you can. Anyway, I've rambled. Other questions? Anyone developed a question yet? Seems all right. Okay, and so this thing is being told by the first part. The second thing is being told by the second part. And so the third thing there is what we haven't explored, which is what a point of inflection is. And so that third thing is telling us what a point of inflection is. And so let's hone in on this red outline part real quick. So the red outline part tells us if the second derivative is 0, that means we have no concavity, right? If the second derivative tells us concavity, second derivative being 0 means no concavity. No concavity is almost, mathematicians love coming up with special cases of things where they don't fit the definition. But in our purposes, in our sort of basic introduction to calculus class, second derivative being 0 is going to mean a point of inflection. And as it says right here, a point of inflection is where the graph switches concavity. So let's just go back up to that first picture that we looked at the start of class that we mentioned last time, right? If we look at this point of inflection, before that, it's concave down, and after it, it's concave up, right? Maybe we can add those words to this picture, right? On this piece, oops, I meant to do that in pen. On this piece, we have concave up. Hopefully you can see that now, right? And on the piece before it, we have concave down. And at the point of inflection, it's switching those two things, right? It's switching from being downward bowl shaped to upward bowl shaped. And so the point of inflection is going to be where the second derivative is 0. So now we hopefully have a good understanding of everything on this graph. And I would like to add a few words to this definition as well. All right, so let me add a couple notes on this page here. So here's what a point of inflection is. Maybe we can add a little box. I'm going to write a few things in here. So let's draw a couple point of inflections. So point of inflection could be like this, or like this. These are the ones that are on the first page. But it doesn't have to be like that. And the reason I want to draw a second one is because sometimes point of inflections can look like something like this, for example. Right? Do you agree that this right here is a point of inflection? Because right before that point, and let me zoom in on this picture, right before the blue A, it's definitely downward curved, right? And right after the blue A, it's definitely upward curved. And so it's a point of inflection in the middle. The difference is in the first derivative at those points, is what I'm trying to point out here. So let me just sort of let everyone write that down, and then I think it's important again if everyone's sort of watching for this last part. The questions about how each of those three graphs that are on the page right now, how those are points of inflection. We've changed the curvature at those points. The thing that I think is important to note is that on the places on the left, the first derivative is 0 because it's flat, and the second derivative is 0 because it's an inflection point. So both the derivatives are 0 on the left. On the right, the first derivative is not 0, it's negative because the function is decreasing there. So that's actually not going to come out of, it's not a critical point. But the second derivative will be 0 because it's an inflection point. You see that? And we'll explore these in some examples and things. But what I'm trying to point out is points of inflection are not always going to be critical points because they're not always going to be situations where it's a flat point, like in the blue graph on the right. Thoughts about that? See what I'm trying to say there? And so just in the last minute, actually, let me let people finish writing this down, and I'm going to graph something real quick and then illustrate. I'm going to graph this picture at the bottom here so I can draw the picture, and then we will end on this example. I just want to draw the picture real quick. Good. Okay, that's what I thought it looked like. Questions about this, what I've written here? Kind of questions about concavity or what I'm saying there? Just going to highlight the point here with this the last example. Anything in the chat? Okay. So just real quick then, let's just draw this picture. And I just did it on my computer. And when I draw this graph, it looks like this. Let me make sure that's right, actually. Yeah. It kind of does this kind of thing. That's what this g of x function looks like. And so it has a max and a min, just looking at the picture, right? There's a max on the left side, there's a min on the right side, and there's got to be a point of inflection between them because we got concave down switching to concave up. And so just, we're not going to do a full analysis here, but I just want to point out to kind of illustrate, first of all, that this graph here is kind of like the right-hand graph. It looks actually very similar to that graph, right? And so notice how if we take the derivative of this thing, which again is a nice easy power rule, if we set that equal to 0, we get 2 critical points, and that's going to be the max and the min. Question, John? Anyone? Okay. And so I'm not going to do it, but you can prove that these are the maxes and min using the first derivative test that we just did. And you can just look at the graph to be convinced. All right, if you don't believe me, you can graph it, but this is the minus square root of 1/3, and then the plus 1 is on the other side. But notice how the point of inflection did not come up on this analysis. That's sort of the takeaway I'm trying to say is that sometimes they come up on the critical points, like this example in the middle from the last time, right? When we did this one a second ago, we ended up finding the point of inflection because it happened to be one of those flat points of inflection. But on this one, it's not a flat point of inflection in the middle, and so it doesn't come up as a critical point. If we want to actually find the inflection point, we need to take a second derivative and set that equal to 0. And so that's all I'm trying to point out here is to find the point of inflection. You can set the second derivative equal to 0. And so if we take the second derivative, it's a g though, not an f. Second derivative is 6x. Set that equal to 0. We find that x equals 0 is the point of inflection. And again, you can see that on the graph, right? Right where it crosses the y-axis is where it kind of switches concavity. So x equals 0 is the point of inflection. And again, just look at the picture and hopefully you agree with that. Okay. So we've got our test next Friday. We're making headway towards that, and got the homework due on Friday, which will be, I believe, the last homework sets before that next test. And so I put lots of topics up there, and I'd love to start to see if there are any questions about homework. If you've got some homework questions, we can definitely start with that. Are there any homework questions? Oops, I've lost the chat here. Let me get the chat out. There it is. Okay. Okay. We're kind of in the middle of the material that'll be on the homework. So, if you want to bring some homework questions for Friday, that'd be great too. But what we were talking about, I guess I should take that out. What we were talking about was we looked at the first derivative test last time. Actually, just realized if we touch the screen, that goes away. Wish I realized that earlier. The first derivative test lets us, well, let me start over a little bit earlier. Critical points are either where the derivative is 0 or where the function or the derivative don't exist, right? So we're looking for flat points or locations where there's a discontinuity. And then the idea is once we find those flat points, we need to figure out what kind of flat point are they. Are they a max? Are they a min? Are they a point of inflection? And so that's where the first derivative test came in, right? The first derivative test gave us a way to plug points in around the derivative and figure out whether or not the function was increasing or decreasing. And that leads us to figuring out whether or not it's a max or a min, or a point of inflection, right? We learned what a point of inflection was in those cases. That's like these are a special kind of flat point that keep increasing or decreasing. And what we learned in the last class was that has to do with concavity, right? And so concavity is the curvature of a graph, which means it's either shaped like a bowl, kind of, right? It has that upwards curvature, or it's shaped like an upside down bowl. So it has a downwards shaped curvature. And it turned out we learned that the second derivative tells us about curvature, right? And so just what we had seen last time in the middle here, I've already got some highlights, but if I do it in red, what's inside there was kind of the main takeaway from the last class, which is if the second derivative is negative at a point, it means concave down. And if it's positive, it means concave up. And if we get the second derivative being 0, that's a point of inflection. And the last thing we kind of ended with was reminding ourselves what a point of inflection actually is, right? So we wanted to find the point of inflection on this last problem. We take the second derivative and set it equal to 0, because that's where it's going to tell us the concavity is changing. And we saw that x equals 0 on this last one was where that happened to happen. So, okay, that was my quick summary. Are there any questions about anything before we get started and keep going with, this next class is mostly going to be about the second derivative and concavity. And we're going to put it all together towards the end and do kind of a more complicated analysis of a rational function here somewhere down the line. I'm hoping I think we should get to this more complicated function, and we're going to take a whole page, maybe more, to think about that one. Okay, let me pause. Thoughts, questions about anything before we get going? All right, so like I said, we're just looking at concavity for the most part, and so we've got another kind of simple polynomial. Most of the stuff early on in the notes, at least, has to do with easier looking functions, right? And so let's look at this polynomial function and think about the concavity at 2 specific locations. So that'll be the first thing we do. And then we'll think about where does it actually change concavity, right? So there's 2 things to look at here, and we'll also provide a little picture as well. Let's just provide the picture first, just so sometimes it's nice just to have the answer before we even start. And so it looks similar to the last graph. It's got that x cubed kind of shape, except it does this. That's not quite right. Stays above the x-axis on the right, and so it has a point of inflection somewhere in the middle that I'm just going to highlight in red. Right, changes concavity somewhere in the middle there, kind of similar to the last one. And we'll think about where that happens and then what the concavity is on either side of that, which involves taking a couple derivatives, which is easy here, right? It's a nice, easy power rule, and so we can easily take a first derivative just using the power rule. and we can take a second derivative just as easy. And I'm hoping by this point, I can kind of take a couple power rules without it being too confusing. But by all means, let me know if there are questions about that, right? Just bring down the power, multiply the power, subtract 1 off the power. And as we've learned, the first derivative tells us increasing, decreasing. And now what we're exploring here now is the second derivative will tell us something about concavity. And so we're specifically asked about the concavity at 3, -3, and 0. And so all we got to do is just plug those numbers into the second derivative, and we've got it. All right, so I'm going to take the second derivative that we just calculated, plug in -3, and we'll also plug in 0. Just right into that function right above there. When you plug in a -3, we'll get -18 plus 2, which is -16. And then 0 plus 2, which is 2. Right, so we get a positive number and a negative number. And that tells us the concavity there, right? Positive means concave up, negative means concave down. And so that's sort of the final takeaway is, okay, well, 16 is a negative number. That means concave down. And 2 is a positive number. That means concave up. And we can just look at that right at the graph, right? If we kind of note where these points are on the graph, -16 is going to be somewhere over on the left-hand side where it's concave down. And 0 is just past the inflection point, right? 0 is kind of right at the origin, and it just starts being concave up, kind of right before that. Okay, thoughts about that? That's sort of the general idea. Tells us about concavity. So we've answered the first question there. What's the concavity at those two locations? Just take a second derivative and plug the point in. Positive means up, negative means down. Very similar to the first derivative. Instead of talking about increasing, decreasing, we're talking about concavity here. Is that okay? So the second part, where does it change? Right there, that's a question that can be phrased a couple different ways, and I want to make it clear what else that's asking. So that's asking, where is the inflection point? If you want to take a look at what inflection point is, we define it, I think, right on the previous page. I don't want to slide up, but you can slide up. So that's the question there. And what we learned on the previous page is it occurs wherever the second derivative equals 0. Right? So this is really just saying, hey, where's the second derivative 0? That's going to tell us where this red dot is right here. Right? It changes somewhere right around 0, but a little bit on the negative side. And so just take the second derivative and set it equal to 0. And when it's a polynomial, especially one like this, that's just a linear function, it's not too bad. But we'll see second derivatives can be complicated, especially maybe it's a trig function. It could potentially be an exponential. That's where we need to rely on some of the stuff. Hopefully we've retained some from some past classes. But anyway, let's do that one right here. So let's take the second derivative down here, which was 6x plus 2. Just set it equal to 0 and solve for x, and we get the answer there, right? X ends up being -2/6, which is -1/3. And again, you can kind of see that over on the picture there that we sketched. I'm going to label that. Hopefully you can see that I have labeled this right here. And we can just see that at -1/3, I should throw the minus sign on there though. -1/3, the inflection point occurs, right? And so this is the point of inflection. And just to be very clear, i.e. the concavity changes. That's what that means. In this case, change from down to up. And we know what changed from down to up because we plugged some points in and saw that in the first part. Thoughts about that, or any of the work there, the second derivative, what I'm trying to say about the second derivative and what it tells us? Okay, so hopefully you can see then that we can use the second derivative. Maybe I don't even need to tell you this to figure out maxes and mins too, right? So that's where the second derivative test comes in, which is the next part. And like it says in this part right here that I'm kind of scribbling on, it talks about when we find these critical points, that just tells us a flat spot, but we don't know whether it's a max or a min or a critical point. And so what we had seen previously was you can use the first derivative test to figure that out, right? So like it says right here, the first derivative test is a way to classify critical points. And the second derivative test, therefore, is another way to classify critical points. And we just do similar kind of things here, but it's a different interpretation. So let me just add that quick note. So second derivative test is a second way to classify critical points. And I would just say compare it to the first derivative test. And you got to know them both. There's two different homework sets. They each get into each one. Oftentimes on tests, I'll specifically ask you to use one or the other. I want to know that you can do both of them, obviously. And so it's pretty straightforward. So let's dig into what it says inside the box right here. So it says, suppose the first derivative is 0, i.e. it's a flat spot. That's what that means. The first derivative at a point is 0. So we're at a specific point here, right? X equals C. So at C, we've got a flat spot. And then the following three conditions is how we classify it. We either have the second derivative positive, the second derivative negative, or the second derivative 0. And each one of those tells us something, right? If the second derivative is positive, we've got a min because we've got a flat spot and it's concave up, right? That's what it would look like in that case. Flat spot, concave up, it's got to be a min. If the second derivative is negative at a flat spot, that looks like a max, right? Because we've got a flat spot, but it's concave down. And if the second derivative is 0 and the first derivative is also 0, that's a point of inflection. And so that would be those special cases that we saw. Remember, I drew this picture last time on the right here. That was that special case on the left, right? Where you have the first derivative 0 and the second derivative 0. That's these special kind of inflection points that look like this. They end up being either this, right? That would be the C location, or like this, right? Again, flat spot and concave down, or sorry, no concavity. So one of those two things. So it's just a second way to classify these things. It involves taking a second derivative, which can sometimes be complicated, but instead of making a table, testing points on either side, you just test one point. You just test the critical point itself. And so that's kind of nice in that you don't have to plug many things in. So there's a trade-off there. Okay, any thoughts about what I'm trying to say there? We will look at a couple. I'm going to ask you to try one. And then I think we'll have time to look at a complicated one. Maybe we'll save that for Friday, that one. We'll see how it goes. Questions? Seems okay? Okay. So we're going to look at this first example, classify the critical points using the second derivative test instead of the first. Is this the same one we looked at last time? Let me just double check this one. Minus t plus 1. Yeah, so this is the same one that we saw, just to be clear, right here. It's the same function. And so the reason I'm pointing this out is because I'm not going to go through the critical point part again. We did the critical points and we found them right here. Okay, and so if you want to double check the critical points, go back up here and see that part. So I'll make that note, but just know that's why I'm going to skip this. So from last time, what page was that? Page 34. So on page 34, you can double check this work. But what we found last time was the first derivative was this. And we set it equal to 0, and we found the critical points. They were 1/3 and -1. Okay, so I'm just going to skip that part because we saw that last time. And if you want to see what they were, you can look up at the page 34, but we found 1/3 was a min and -1 was a max. And so let's just sort of verify that, classify them using the second derivative test. And so if that's the first derivative that we just wrote down, let's use the second derivative test here. So let's take another derivative. It's an easy chain rule again, no problem. And then instead of making a table, we just plug the critical points themselves in, and it's super easy, right? So the second derivative with 1/3 plugged in. All right, if I could work on my writing today. And we'll do the second derivative with -1 plugged in. And similar to the first derivative, we don't really care what the value is, right? The value will tell us something about how concave it is, but all we really care about is whether it's positive or negative, because that'll tell us whether it's facing upwards or downwards, right? So when we plug 1/3 in, we end up with 2 + 2, which is 4, which is a positive number. And when we plug in -1, we'll get -6 + 2, which is -4, of course, which is a negative number. And so we're verifying these two things that we already found last time, which is this positive number means we have concave up at 1/3, and that implies we've got a min. Just a different way to kind of reach that conclusion. And the opposite happens with the other one, right? We got a negative number, that means concave down at that location. And so that means we've got a max there. And remember what we saw last time. If you want the actual maximum or minimum value, you have to plug that back into the original. And so I'll make that note in 1 second, but let me just sort of pause, let folks catch up and see if there's a question about any of that work. And when you start, again, these are all polynomials, so they're kind of easy in some respects. Just the power rule, setting them equal to 0 and solving is easy as they get, at least. When you start having the other ones is maybe where it gets a little more complicated. And so that's where I'm hoping some folks will start looking at the homework, and we can look at some of those in class. Looks like, well, let me let you catch up and see if there's a question. I'm just going to double check the homework and see how people are doing on that. My guess is most folks haven't really started it, which is fine. Questions?
You said the homework is due Friday, Professor?
It is due Friday, yep.
All right, thank you.
Yeah, most folks haven't started looking at that, so that's why there are a lot of questions, which is fine. We can look at it on Friday, but I don't. The homework due on Friday is kind of unfortunate sometimes, and so the only reason that happened is because I ended up postponing it one time from Wednesday, and we just got in that groove. So I was hoping we could do it a little sooner and talk about it today, but it's okay if you want to talk about it Friday. All I'm trying to say is maybe just look at it before Friday so you can see if there are confusing ones so we can go over them. That's all. Questions about the work here at all? Okay, the last thing I'll just remind you of, we haven't found the max of the min, and I'm not going to find it, but I just want to clarify, sometimes questions ask that. And that's really what matters, right? If this is a problem we cared about, this function, this t³ function, was some function we cared about, like the population of an animal or something, and we wanted to know what's the biggest it's ever going to get, what's the smallest it's ever going to get. We found out where those happen, but if we want to know the actual values, we need to plug them into the original. And so I just wanted, it's important to write down, because you'll see this in homework, the min value occurs at plugging in the min into the original, right? So you would plug 1/3 into the original function h of t. And the max would be at whatever the value is at -1. Just want to make that clear, just so it's all clear what we're doing here. We're finding the max and the min where they are. If we actually want them, we got to plug them in. Okay. I'm going to do this next one because it's a little bit trickier. It's no longer a polynomial. And so this will be our first sort of exploration into one that's not super, super easy. We're going to have to rely on some past algebra. And so it's okay to ask questions about that, but just know that digging into some, past solving equations is going to be important. All right, nothing to clarify right now. Okay, so let's do this one. Same kind of idea, except now it's not a polynomial. And so the way we think about this one is being the second term there is really 9x to the minus 1. And we want to do that because when we take derivatives, it just becomes a power rule if we do that, right? If you wanted to leave it the way it was, you could leave it the way it was and then do a quotient rule on this one. But that's just going to be nasty. And the 9 is a constant, so it ends up going away anyway. And so it's just more work to do a quotient rule. I think it's if we just kind of think about it as a power rule, simplify things a little bit. So let's take some derivatives. So we're going to find the critical points, right? Critical points happen where the first derivative is 0. So we take the first derivative, and it becomes 1 minus 9x to the minus 2. See if that makes okay, right? X becomes 1, bring down the power, subtract 1 off the power. And we want that to be 0. We're trying to find the critical points. And so let's solve that equation. What we want to solve is this equation, right? Just pause there and see if that looks okay. I want to take this slow enough for people who are following along with the exponents and everything. That's all right.
How did you get the -2?
So I just did the power rule on this term.
Oh, okay. I got it.
All right. And so when you subtract 1 off of -1, it becomes -2. Yeah.
Okay, thanks.
Yeah, those negative exponents, be careful with them, right? If you had something like 1 over x cubed, which is x to the minus 3, if you differentiated that, bring down the power, but then when you subtract 1 off, we're used to like, oh, the 3 becomes a 2, but no, -3 minus 1 would be -4, for example. So being careful with those negative ones. Other thoughts or questions? Seems okay. So we add the negative term to the other side and we get that. And there's a couple ways we can solve that. It's a nice easy one. And so we could cross multiply, right? This is like a 1 over 1. That's sort of the thing that I feel like people usually go to. Or just multiplying both sides by x squared is going to do the same thing. And so either one of those things, if I cross multiply, for example, it just becomes this, right? So from here to here, just cross multiply. So this is, solving fraction equations or rational functions, rational equations. And then we just take a square root. Right? X squared equals 9. Take a square root. How much room do I have here? I guess I can. Just going to go up here with it. Right, when we take a square root, we get plus or minus. Remember that. So that's two things. And I'm sort of, we're not going to go over all this algebra stuff, but solving a rational function, you multiply by denominators to get rid of them. And then if you take a square root, you get plus or minus. So those are two of the critical points. It's okay. Since this is also the first non-polynomial, it's also the first one that has discontinuities, right? Every single previous time when we did critical points, I always wrote down things that were like, oh, we don't have to think about, right? They're polynomials, so there's no discontinuities. Polynomials, no discontinuities, and I was harping on that for a reason because now we have some. And so let's just think about that real quick. So also, the function and the derivative have what discontinuity? Right? You have x in the denominator of both of them. So what can't we plug in?
0.
0. So that becomes one of the critical points. And so both the things I have boxed in right now are critical points, or all three of them, I should say. So to kind of take the final critical points. Critical points are at 0, which is a discontinuity, -3, and 3, which are probably maxes or mins, or maybe points of inflection. All right, is that okay? We're going to classify them. That's the last step here.
I have a question about how you cross multiplied to get 9 on the other side.
Sure.
I don't really understand it.
So you're familiar with the concept of cross multiplying when you have like two fractions that are facing each other? Or does that word not make, does that phrase not ring a bell? So all it means is, zooming in on the fraction, the denominator of one multiplies the numerator of the other, like this. And that, so 9 times 1 is 9, x squared times 1 is x squared.
Okay.
Does that ring a bell a little bit? The other way to think about it is, and it depends on how you like it, I teach it both ways when I do pre-calc. You can multiply both sides by x squared, right? If I multiply this side by x squared, multiply this side by x squared, they cancel over here, and then you also end up with x squared equals 9. So we're trying to get the x out of the denominator, right? That's sort of the way to think about it. How do we do that? We got to multiply. Yeah, other thoughts, other questions, clarificational things like that? Those critical points seem all right. So this, this is specifically asking us to use the second derivative test. And you oftentimes see something specifically telling you to do one or the other. Let's try to get rid of this here. Come on. Now the thing's back on the top and it won't go away. It's amazing. Go away. There we go. Okay. And so let's classify them. That's the last step. Well, x equals 0 is very clearly a discontinuity, right? Because it came from dividing by 0. So that's not one we need to plug in anywhere. Or if you tried to plug it in, you'd get errors in your calculator and stuff. And so that's just another indication it's a discontinuity. And for the other two, let's just plug them into the second derivative because we're being asked to use the second derivative test here, right? So let's take the second derivative. It's another power rule. And so if we think about the power rule again, we just get 18x to the minus 3. Is that okay? So power rule on this piece. Let me know if that looks all right. The 1 goes away. Minus 9 times minus 2 becomes 18, right? Subtract 1 off the power, becomes more negative. It's okay. Which, as a reminder, looks like this. It's like 18 over x cubed. And maybe it's easier to plug it into something like that, for example, right? And so when we plug in 3, we get 18 over 27, which is positive. And when we plug in -3, we'll get the same thing, but negative. And so one's going to be a max, the other one's going to be a min. And let's sort of take that away. And we'll draw a graph right here. So leave a little bit of room, maybe. We'll draw the picture right here. So let's just kind of finish this off. So positive second derivative means concave up. And so that means it's a min. And then concave down means max. And we could have found the same thing using the first derivative test. So if you really wanted to have some fun, or maybe check your understanding is what I really mean. Maybe you could try the first derivative test on the same problem and just see if you can verify that. It's good practice for a test or something. Let's throw down the plot real quick. So I plotted this on my calculator. And it looks a little something like this. So there is a discontinuity at 0. So there's a dotted line at 0. Let's throw that in. Oops, I just wanted that to be a line, but it looks like a line enough. And then it turns out it does a funky thing on either side of the line. It does this kind of thing. And it does this kind of thing. And so there's this max at -3, and there's this min at 3. That's g of x. And graphing, I always try to draw a picture, assuming I've got room. Graphing these things is a good thing to do. Busting out a calculator or going to some website like wolframalpha.com while you're doing these homework assignments. That's what I would do, right? You can just look at the picture and see the answer, and then use math to kind of verify that answer. Or if you mess something up, you're not getting a web work question right, graphing it is a great way to see whether you have the right answer and you're just not entering it right, excuse me, or there's something wrong with the math, right? All right, any thoughts? Any questions there at all? Okay. So the next one is the one I'm going to let folks work on and see how you can do. I'm going to break folks up into breakout rooms, but I'm going to sort of set up the idea first. And if you happen to be watching this later, not live, just work on it yourself during the breakout room. But I just want to set it up just so we're not confused about the derivative, because sometimes people get confused about the x to the 6 over 3. I did that so that when you bring down the 6, it'll turn into a nicer number and not have fractions and things. That's the only reason there. So yeah, let me just take 2 derivatives on this next one, and then I'll let you think about it for a little bit. So we have this function g. It's another polynomial, so we're not going to have discontinuities. Keep that in mind. And the instructions here say find the critical point. So that involves the first derivative. And then we're going to classify them using the second derivative. And then there's an additional step, which I'm not going to sort of talk about. I'm going to let you think about and then go over, which I think you should be able to figure out basically based on what we've talked about, which is figuring out where the function is concave up and down. Like what intervals is it on, right? So the second derivative tells you can use it to tell when it changes concavity. And so then use that piece of information to think about when is it concave up and down overall. So that sort of last question is something to think about together and see if you can come up with an answer, and then I'll go over it. But I just want to start us off with just taking the derivatives together just so there's no confusion about that. It's an easy power rule again, and it becomes 2x minus, bring down the 6, divide by 3, it becomes 2. 2x, what just happened there? It'll be 2x to the 5th. And then the second derivative is an even easier power rule, which is just 2 minus 10x to the 4th.
Professor, how did you get minus 2x to the 5th again?
So when you bring down the power on that one, actually, let me look at this one. It'll be minus.
You can put 1/3.
1/3, yeah, that's right.
I got
Times
you.
6 times x to the 5th. And so when you do 1/3 times 6, or 6 divided by 3, that's where the 2 comes from.
Okay, that makes sense.
Other thoughts about that? Seems okay. Setup's okay. So you're going to find critical points, which involves setting the first derivative equal to 0. Looks like it's going to be a factoring problem. and then take a second derivative to classify it. And then again, thinking about where concavity occurs also has to do with the second derivative, and I'll just sort of let you ponder that for a little bit. I'd like to spend at least, I'd like to come back to this probably around, so we're back. Just checking in with some of the answers here. So I know everyone got the critical points. I checked in with everyone about that. And I also have the classifications down there right in the middle. And so for the classifications, specifically using the second derivative test, we want to plug things into the second derivative, right, the critical points. And when you do that, we also previously had the second derivative, right? So you just take those, plug it into them. Easy polynomial, so no big deal. And when it's a positive value, we have concave up, therefore a min. Negative value means concave down. So we have the 0 being a min, the midpoints or the endpoints there being maxes and maxes, which seems kind of strange, I feel like, when you think about both those points being maxes. But we'll also draw the picture in a second here. So let's leave a little bit of room for, say, the picture right here. Classification, okay. I'm also going to answer that last question about where the concavity changes. Thoughts? Love the cat, Mariana. Love it. Okay, so if we want to know, the last question, where is it concave up and down? The question is, where does it switch, really? Right, so let's take the second derivative and find the inflection point. And so it's 2 minus 10x to the fourth. Just set it equal to 0 and find the inflection point. And so it involves like adding the 10x to the fourth the other side, dividing by 10, taking a fourth root, right? So I guess I'll do the intermediate step. It ends up being like x to the fourth equals 1/5. When we take a fourth root, we get plus or minus fourth root of 1/5, right? And so these are the inflection points.
So to find the inflection point, you you take the derivative of you make the derivative of the derivative equal to 0.
Yep, that's right, the second derivative. And so just to kind of, I tried to flesh that out here, for example, right? Just so you can highlight where it says that when the second derivative is 0, we've got an inflection point. And it also kind of fleshed it out a little bit right here when we, if it's 0, it's either concave up or down, which usually means that's an inflection point. So just kind of looking back, the last from about page 35 where it starts saying concavity through this page is really where we're thinking about all this stuff, this material being. Yep, other questions? Thank you for that question. Okay, and so plus or minus fourth root of 1/5 are like numbers that are really close to 0, right? And so we're going right on either side of 0. And so it turns out we have points that we've already tested around that, right? From the classification right up there, those are points that are on either side of this. And to kind of maybe give you the picture a little better, let's start to draw our graph, or let's just draw the graph. I'll show you what the graph looks like. So I plotted it. Did anyone plot it themselves? Did you think about doing that? It's always a good idea. I've got it on my computer. Let me just pull it up real quick so I can remind myself. So it goes between like -2 and 2, and it looks like this. Right, so this is g of x. And so you can see the things we just found, right? So this point right here where the max was -1 and 1, and then that min is supposed to be right at 0, that bottom of the hoop there. And you can see the inflection point, right? The inflection point, let's just highlight them in red, plus or minus fourth root. It's like right here and right here. I don't know how we want to note that. The inflection points are those two places. Is that too messy? I don't know. See that though? See how it's concave down on one side and concave up in the middle though, if you kind of put the dot there. And so that's sort of what we just found. And so if we want to think about the interval on which it's concave up and down, looking at the picture and the points we already plugged in, we know the answer to that, right? And so So let's see, how can I make this stand out? I'll do it in black. And I'm going to say, based on this information, so I'm going to draw an arrow down here. So based on plugging things in around the inflection points, we know that it's concave up between, in the middle there, right? So from the 4th root of 1/5, from the minus of that, excuse me, to the plus 4th root of 1/5. I know those are weird points, but that's that middle part. And then it's concave down on the other parts. So it would be minus infinity to the first one, union, and then past the first one, right? So 4th root of 1/5 on. Because we plugged in points around there. I know I kind of ran out of room, so I don't want to, I can't jam it. I guess maybe let me just make a note here, actually. Can I do that? Okay, sorry. I'm done here. I just wanted to make this clear in case anyone's confused. So we know that the inflection points are here and here, plus or minus that. And we tested points from above in green. We had tested 0 and plus or minus 1 in the second derivative, right? And we found that it was, let's see here, it's concave up in the middle. And then it was concave down on the outsides. And I will erase this in 1 second, but I'm referring to this work right here, and I'm talking about this. Right, we had tested points around those critical points, and we knew the inflection points were at the middle. I guess maybe that's the thing that's maybe I want to be clear about. The roots are the inflection points. We tested points around them, and so we know what changed at those points, and we just know that it has to be the other things in between them. So it's sort of like doing the second derivative or the first derivative test on the second derivative test. So this is kind of like this is similar to the first derivative test, but with the second derivative.